In this video, we'll talk generally about non-homogeneous linear equations of second order and how we might go about solving them. So the most general second-order linear non-homogeneous equation is of the following form. It's y double prime plus p of t times y prime plus qt times y equals g of t for some p, q, and g functions. These will seem to be nice continuous functions where they're defined. And the main thing we're concerned about here is when g of t is not 0. If g of t is 0, then it's a homogeneous equation. We know how to solve those. We've been dealing with those so far in this chapter, particularly for constant coefficient ones. But now I want to think about what happens if this function is not 0. How does it being not 0 change what the solutions look like and change how we go about solving them? To think back to solving homogeneous equations, the main idea was that for those equations, we always ended up with a c1 times some y1 plus a c2 times some y2 of t. That was the general form of these solutions. We'll see in a bit how this equation being non-homogeneous changes this slightly. And the idea for solving these really routes back through the homogeneous equation, because at least for the constant coefficient cases, we know how to solve them. Right, if we had just a y double prime plus by prime plus cy equals 0, we know how to solve that one. We have methods, we know what we're doing, we find the roots, we solve things out. All that works the same way for this type of equation here. But what if this is not 0 and is some function g of t instead? How is that going to change how we go about solving this problem? Well, if we get back to the equals 0 case, we'd be in good shape. So let's see what we can do with that. Let's start with saying that we end up with two solutions to this non-homogeneous problem. Now, these y1 and y2 are solutions to the non-homogeneous equation. They are not our fundamental set of solutions from before. But assume we have these two. Then what can we do with this? Well, this means we know the following. This means we know that y1 double prime plus p of t y1 prime plus q of t y1 equals g, as does the same for y2. So I can subtract these two equations. And if I do that, I will get that y1 double prime minus y2 double prime plus p of t times y1 prime minus y2 prime plus q of t times y1 minus y2 equals 0 because the g of t's cancel out. But then the derivative is linear, which means if I look at y1 double prime minus y2 double prime, that's the same thing as y1 minus y2 double prime. Similarly, this is p of t times y1 minus y2 prime plus q of t times y1 minus y2 equals 0. Or what's going to be important looking at this, if I define a function u to be y1 minus y2, I then have that u double prime plus p of t u prime plus q of t u equals 0. As in, this u will solve the corresponding homogeneous equation, where I have 0 now on the right-hand side. So if I have two solutions to the non-homogeneous problem, I know for a fact that their difference will satisfy the corresponding homogeneous problem. And that there gives rise to the following theorem, which says exactly that. If I have two solutions, y1 and y2, that solve the non-homogeneous equation with the g of t here on the right, then their difference solves the corresponding homogeneous equation now with a 0 on the right side. So great, what does that do for us? Well, at least for constant coefficient equations, we know how to solve the homogeneous part. We find the roots, we do the exponential things, we get to our solutions that way. So a way we can interpret this is that if I know the difference of these two solves the homogeneous equation, then I know that in this case, y1 must equal y2 plus what I'll call y sub c, where this y sub c solves the homogeneous equation. It is sometimes called the complementary solution. And this works for any functions that solve the non-homogeneous equation. So it means that I can get from any one particular solution to the homogeneous equation to all other ones just by adding something that solves the homogeneous equation. Which means I only have to find one of these guys. if I find a single function that solves the non-homogeneous problem, I can then get to every other solution, which you think about as I could get every other initial condition, just by adding a solution of the homogeneous equation, which I already know how to solve. So we just need one solution to the non-homogeneous problem. And then can write a general solution is going to be something like this y sub p, which is going to be our one guy that solves the homogeneous problem, and it's called the particular solution, plus this yc part, and we know the form of the yc. It's a c1 times our y1 of t plus c2 times y2 of t, where here I've gone back to y1 and y2 being the fundamental set of solutions to the homogeneous problem. So we know that our general solution is going to look something like this for any yp that we find, and then we can use the c1 and c2 from the homogeneous part to do initial conditions. So as long as we find one of these yp, we're in good shape. There's a lot of functions that would work, but if I find one in particular, that'll give me enough to be able to set up and solve this problem. And in future videos, we'll look at examples of ways that we can go about trying to find this yp for a given situation.